Hello everyone, and I once again welcome you all to the JCE Connect and online lectures of precious concrete structures. So, in online lectures of precious concrete, we were discussing about the shear strength of precious concrete beams. Okay, and we have solved the number of problems, and today's session also we are going to solve the examples over again to compute the shear strength of precious concrete beam. Okay, so it is given as a precious concrete beam having unsymmetrical I section has a fiber stress distribution of 13 Newton per mm square, that is compression, nothing but at the top edge, okay, and linearly reducing to 0 at the bottom. Top flange is the size of beam, it is the top flange 2400 mm by 400 mm, bottom flange 1200 mm by 900 mm, okay, and web is 1000 mm by 600 mm. The shear force acting on the beam is 2350 kilonewton. Okay, then calculate the principal tensile stresses at the centroidal axis at the junction. What? Calculate the principal tensile stresses at the centroidal axis and at the junction of the web with the lower flange. Okay, so here it is a unsymmetrical I section. Okay, the beam is unsymmetrical I section, and they are given the stress distribution in the beam, that is at the top flange. So always when the beam bends, so the top flange will be under compression and the bottom flange will be under tension. So they are given the stress distribution in the beam. So 13 Newton per mm square, that is compression obviously at the top edge, means at the top flange, and it is linearly reduced to 0 at the bottom flange. So there is no tensile stresses here at the bottom flange. Then top flange size is 2400 by 400 mm, then bottom flange 1200 mm by 900 mm, and web thickness is, the web size is 1000 mm by 600 mm, and the shear force is 2350 kilonewton. Okay, then we have to calculate the principal tensile stresses at the centroidal of the section and at the junction of the web and the lower flange. Okay, so here we have the sketch according to the above mentioned. Okay, so the top flange, you can see the width of the flange is 2400 and the thickness of flange is 400 mm. The bottom flange is width is 1200 mm and the depth is 900 mm, and the web, so this part is web. Okay, so I can, here this is a top flange. Okay, and this is a bottom flange. Okay, and this is a web, this part is a web. Okay, the web size is given as 1000 mm depth and the thickness of web is 600 mm. Okay, so this is regarding the sketch or the cross section of unsymmetrical I section. Okay, then they are given the stress distribution here, the stress distribution according to, okay, so the compression and the tension. So we have the compression is 13 Newton per mm square and it is linearly reduced to 0 at the bottom flange, and we have to find out the principal tensile stresses at the centroidal axis and at the junction of the web and the bottom flange. Okay, so we will start with the solution here. Okay, so here first of all we have to find out the location of centroidal axis or the location of centroid. Okay, so because it is an unsymmetrical I section, so we have to locate the centroidal axis. Okay, so first, okay, so that is location of centroid, that is location of centroid. Okay, so we know that it is calculated by summation of a into y divided by summation of area. Okay, summation of a into y divided by summation of area. So here we'll divide our section in three parts, that is top flange, web and bottom flange. 1, 2, 3. So because of that, what will happen? So it will be a1 y1 plus a2 y2 plus a3 y3 divided by a1 plus a2 plus a3. Okay, so here, so we'll find out the y1 y2 y3 first, so later it will not be problematic. So y1 for bottom flange, so that is 900 divided by 2 directly, because we are calculating with respect to the bottom axis. Okay, so what in y1 is 900 divided by 2, so 450 mm. So y2 for web, so it is 900 plus 1000 divided by 2, so it is 1400 mm. Okay, and y3, okay, so that is 1900, that is 1000 for web and 900 for bottom flange, and up to the center means it is 400 divided by 2, so it will be 2100 mm. Okay, we can see here, I'll just explain here. Okay, yes, here you can see. So we are calculating with respect to the bottom axis. So first, for bottom flange it is 900 divided by 2, 900 divided by 2, and for web it is 900 plus 1000 divided by 2, and for the top flange it is 900 plus 1000, that is 1900 plus 400 divided by 2, and what we have calculated here we can see here. Okay, so 900 plus 1000 plus 400 divided by 2, so this is regarding y. So therefore y bar is equal to a1 y1, so a1 is 1200 into 900 into y1 is 450 plus a2 y2, so that is 1000 into 600, so that is web, and y2 is 1400 plus y3 a3 y3, so 2400 by 400 into 2100. Okay, so that is a1 y1 plus a2 y2 plus a3 y3 divided by summation of area, so that is 1200 by 900 plus 1000 by 600 plus 2400 by 400. Okay, so we'll get y bar is equal to 1265.90 mm. So it will be from bottom, okay. So so we'll locate here, so the y bar from bottom we got it as 1265.9. so just I'll draw the line here. Okay, so we got it as 1265.9, so I'll consider from it here. We got it as this, so this is the centroidal axis, and this distance from the bottom is 1265.9. okay, 1265.9, we got it as 1265.9. okay, and from top also we can calculate, so that is So from top we will get 1034.1. So I'll locate here. So from top, the centroidal axis, that is 1034.1. okay, 1034.1. from bottom it is 1265.9 and top 1034.1. okay. Then next is, after location of centroidal axis, next is moment of inertia with respect to y axis. Next is moment of inertia okay. So that is Ixx. We have to find out the moment of inertia Ixx. okay. So again, Ixx is I self plus Ah square, I self plus Ah square. okay. So we'll calculate one by one. Again, with respect to the bottom flange, web and top flange. okay. So it is I self plus A square. So I, it is for bottom flange 1200 by 900 cube by 12. okay. So 1900 with respect to horizontal axis Ixx. okay, that is xx axis. okay. B is 1200 and depth is 900. So 1200 by 900 cube by 12 plus 1200 into 900, so that is area, into the h, it is 815.9 square, I plus A square. So I will explain later on. Plus again for web, so width is with respect to horizontal axis xx, width is 600, depth is 1000 cube divided by 12 plus area is 600 into 1000 into h is 134.1 square. Then plus for top flange, B is 2400, depth is 400 cube by 12 plus area into 834.1 square. okay. So whole together we will get at Ixx as 1.53 into 10 raised to 12 mm raised to 4. So we got Ixx is this much. So we'll check out for now this distances, how we got these distances. okay. So first of all, so that is h1, h2 and h3. I can write h1, h2 and h3. So this is, I call it as h1, h2 and h3. So we'll look out how we get h1, h2 and h3. okay. So here, so first of all we can see, okay, this. So again, now the h1 is here the distance from the centroidal axis to the center of this. okay. So distance from the centroidal axis to the center of the bottom flange. okay. So the total is 1265. 1265 minus 450 you have to do, because total is 900. 1265 minus 450. So I can show you here. So 1265.9 minus 450. So it is 815.9. I think we have got same. So what 815.9. So I'll write here 1265.9 minus 900 divided by 2. So we'll get 815.9 mm. okay. So this is regarding h1. Then h2. Now the h2 is again here the distance between centroidal axis to the center of web. The distance between the centroidal axis, okay, the distance from the centroidal axis to the center of web. So that is nothing but h2. okay. So here how you will get h2 then? So 1265 minus 1000 divided by 2 plus 900 means this distance, the CG is 1000 divided by 2 plus 900 minus 1265.9. So I'll just write here H2 is, so H2 is equal to, first of all the bottom line 900 plus 1000 divided by 2 minus 1265.9. So we will get H2 as 134.1 mm. So we have got here 134.1. And then H3 is now directly, we know the centroidal distance from the top flange, that is 1034. So directly what you can do, so this is the distance, that is H3, from center of the bottom top flange to the centroidal axis. Okay, so 1034.1 minus 200. Okay, can calculate. So that is 1034.1 minus 400 by 2. So that we will get it as 834.1 mm. So we have used 834.1. So this is regarding H1, H2 and H3, because H square, A square. So we got it as the moment of inertia is 1.53 into 10 to 12 mm raised to 4. Okay, so next we will move ahead. Okay, so next is calculation of principal tensile stresses. Principal tensile stresses at centroidal axis. At centroidal axis, because the first they are asked to calculate the principal tensile stresses at centroidal axis. Okay, now we will calculate that. Okay, so therefore the direct stress is, first the direct stress, okay, so this is as per stress distribution diagram, as per stress distribution diagram. Okay, so here I'll just draw the stress distribution diagram once again. So the stress distribution diagram is given like this. So here it is 13 and here it is 0. Okay, and at the centroidal axis, the location of the centroidal axis is somewhere, I'll just locate here. So this is 1265.9. So this is 1265.9 from bottom. Okay, now we have to find out the direct stress according to this stress distribution diagram. Okay, according to this stress distribution diagram. So in that it is given the top fiber stresses is 13, the bottom fiber is 0. So by using the concept of symmetrical triangle, so we have to find out the stresses at this location. So we have to find out the stress at this location. So the stress at this location we have to find out. Okay, so according to the stress distribution diagram. Okay, so here I'll calculate. So here I'll calculate this, I'll note it as Fx. So because we have to find out the direct stress at this level. So by again the symmetrical diagram. So this total depth is 2300. The total depth of the beam is 2300. Okay, so by that we can calculate this divided by this, this divided by this. So 13 divided by 2300 is equal to Fx divided by 1265.9. Okay, So therefore we'll get Fx is equal to, 7.15 Newton per mm square. So we'll just check. Okay, we got Fx is equal to 7.15. So we'll check 13 divided by, so you got 7.15 Newton per mm square. Understood? So by using this stress distribution diagram. Okay, so then vertical stress, so we don't have any vertical tendons here or the vertical reinforcement, so therefore the automatically Fy will become 0. So we don't have to calculate that. So next is shear stress. Okay, shear stress. So first is direct stress, then shear stress. Shear stress is again tau V A y bar upon IB. So here again we have to use the standard formula V A y bar upon IB. Understood? So first we know that V is given. Okay, I we have calculated, B we know. So next is important is A y bar, the calculation of A y bar. Okay, so again it is A y bar is A1 y1 plus A2 y2. A1 y1 plus A2 y2, because it is the second moment of inertia, A1 y1 plus A2 y2. Now here again, so I'll just draw the sketch here. With respect to the centroidal axis, we have the top flange, and the web. Okay, with respect to the centroidal axis, x I can say. And here this distance is, we know, I think this distance is, we will check, it is this distance is total is 1034.1. This distance is with respect to the centroidal axis, the portion subjected to compression, so that is above neutral axis, 1034.1. So this, so here again y1 is equal to and y2 is equal to, so y1 is nothing but the center of this to this. Okay, so this will be y1. Okay, so y1 is again 1034.1 minus 200, so that is 834.1 mm. 834.1 mm. So for this, for this area. Okay, now we have to find out for this. So y1 will be for, so sorry, चलिए y2. So y2 क्या होगा, total is 1034 minus, if I deduct 400, if I deduct 400, 1034 minus 400, तो ये कितना हुआ, ये कितना बचा अभी, so this will be 634.1. तो y2 क्या हुआ, y2 will be 634.1 divided by 2. 634.1 divided by 2. So we will get it as 634.1 divided by 2. So this will be 317.05 mm. 317.05 mm. Okay. So again, so this will be 1 and this will be 2. So we will calculate now. A1 Y1, so that is AY bar is A1 Y1, so A1 is, so this is 2400 by 400, so 400, so A1 Y1 is 2400 by 400, A1 into Y1 is, Y1 we have calculated, that is 834.1 plus A2 Y2, A2 is this area, that is 2 from here to here, so that is 634.1 into thickness of web is 600, the thickness of web is 600, 634.1 from here to here into 600 into the distance is 634.1 divided by 2, whatever calculated, that is 317.05. So we'll get AY bar is equal to, 921.36 into 10 raised to 6. Okay, so that is mm cube. Second moment of inertia, mm cube. So after substituting back here, so tau is equal to, we have to substitute in the formula. So V is 2350 V AY bar, so V is 2350, area is that is V AY bar, so that is 921.36 into 10 raised to 6 upon IB, IB is 1.53 into 10 raised to 12 into B, so that is the width of the section at the central axis. B is, so I will write B is width of the section at centroidal axis, so is equal to 600 mm. Okay, because we are considering the section at centroidal axis, because it is given calculate principal tensile stresses at centroidal axis. So B with respect to the centroidal axis, so that is 600. Okay, so we'll get it as 2.35 Newton per mm square. We'll get it as tau is equal to 2.35 Newton per mm square. Okay, so therefore the principal tensile stress is, so therefore the principal tensile stress is F2. We directly find out F2, so that is 7.15 plus 0, so that is Fx plus F4 divided by 2 minus, because it is a principal tensile stress, is minus sorry, it is right, half of, minus half of 7.15 minus 0 divided by 2 whole square plus 4 tau, so that is 2.35 square. So we will get F2, the principal tensile stress is minus 0.7 Newton per mm square. So is what the principal tensile stresses at the centroidal axis is minus 0.7 Newton per mm square. Okay, so then we will calculate. Okay, next they are asked to calculate calculation of principal tensile stress at junction of bottom flange and web, at junction of bottom flange and web. Okay. So again, direct stress Fx with respect to again the stress distribution diagram. Okay, so by considering the symmetrical triangle, so here I'll just show you once again. So we have to find out at the bottom flange. Okay, so so that is, it is at a distance of, so the bottom flange, it will be, the thickness is 900. So here in the earlier case 13 divided by 2300 is equal to Fx divided by this thing. So now it will be Fx divided by 900. Okay, because with respect to the bottom flange, so this is the location of bottom flange, that is 900. Okay, so it will be 13 divided by 2300 into 900. Okay, so we'll get this as 5.08 Newton per mm square. 5.08 Newton per mm square. Then Fy is again 0. So again tau, the shear stress, is tau. Then it is VA y bar upon IB. VA y bar upon IB. Okay. So again AY bar. Okay, AY bar. So it is connected to web with the flange. Connected to web with the flange. Okay. So AY bar you have to find out again. So here AY bar is, so area is, for web it is 1200 by 900, and Y is again it is 1265.9 minus 900 divided by 2. Okay, so we'll check. Yes, it is correct. 1265.9 minus 900 divided by 2, because it is up to the this thing. So 1 2 so that is 815.9. Okay, so up to the center of bottom flange. Okay, so we'll get, so therefore we'll substitute here. So tau is, V is 2350 into 10⁻³ into AY bar, so that is 1200 into 900 into so this is, this will get it as, this term will get it as 815.9. so 815.9 VAY bar upon IB. So I is 1.53 into 10⁻12 into B, again 600, because web is collected with flange. Okay, so we'll get this as 2.25 Newton per mm square. Okay, so that is tau, 2.25 Newton per mm square. So again with respect to this, so the principal stress is F2, principal tensile stress is F2, so that is Fx plus Fy, so that is 5.08 plus 0 divided by 2 minus half of square root of 5.08 minus 0 divided by 2 whole square plus 4 into tau is 2.25 square. So we will get F2 is equal to minus 0.853 Newton per mm square. This is minus 0.853 Newton per mm square. So we have calculated now as per the question, okay, mentioned in the question. So this is the principal tensile stresses developed in the at the location of centroidal axis. So we have calculated that is minus 0.7 Newton per mm square, and at the junction of web and the flange, it is bottom flange, web and the bottom flange, that is minus 0.853 Newton per mm square. So you can see at the extreme fiber, we can see the stresses are more compared to the centroidal axis. Okay, so this is regarding today's session. Okay, thank you. 8.5 0.853